We are recording. Okay. Okay. Hello, people. I would just for the record, I want to point out that I petitioned to have this an actual in-person class. So, and it was turned down. So I would much prefer to actually see your smiling faces there through the glass. And I even though I'm 65, I trust my immune system to sort of do what it was evolved to do, and so on. So I tried, but hopefully in the spring things will start returning a little bit more to normal. Okay, so topics for today. Oh, and one last thing, I'll email you out. I'll email you out some instructions for. If you want some in-person meetings like office hours, I'll send a group email to everybody on instructions for where we can meet. So today, what did we do last time? We did. What did we do last time? I know it's over here. So we had done the dot product, and then we were sort of applying it. Yeah, so dot and cross product. And so what we want to do today is go through some examples of the precession equation. And these, to some extent, they're sort of implied by just putting that equation up. And so what was that equation? So it was the Bloch equation first term. And so that Bloch equation first term was the change, that's D is for derivative, change in the magnetization vector over a small period of time is equal to whatever the magnetization vector is at the current time, cross-producted with whatever the B vector is at the current time. So that was the first term of the Bloch equation. And so what we want to do now is just actually play with that equation. And so one of the things when you have equations like this, they're not very complicated. It's got like, that's a constant, so we'll sort of ignore that. It's got three parts in it. It's only three things. But it's still worthwhile to mess around with it to sort of see what it does. And how you do that is you sort of like change the different values in it, and then see what it does to the output. So you have to sort of operate on it like a little machine in order to really understand it. And so that's what we're going to do today. Sort of like look at how changing these things in the first half, how changing these things sort of affects the output of the equation. So remember we said that. So if this is one vector and this is another vector, so say this is the A vector and this is the B vector. So for example, this guy would be the M vector. And the B vector, for example, that guy would be the magnetic field vector. We said that when you cross product two vectors like that, the order is important, and then the result is that you get a vector that's just sticking out at you that's perpendicular to it's perpendicular to this guy, and it's perpendicular to this guy. So it's perpendicular to the plane between the vectors, and then you figure it out by this thing where you sweep your finger, you figure out whether it's in or out by which side of the plane it's on, basically, by sweeping your fingers from the A to the B, and then your right-hand thumb tells you which direction that C vector is. So this is the C vector. And, for example, dm dt. So And then we went through, last time how you actually how you do the multiplication. But one of the things that we found out about the cross product is that, which we're going to use today, is that if you look at the length of the cross product, so here's the dm dt vector, so that thing means get length. So however many dimensions you have, it means just find the length of the vector and ignore what direction it's pointed in. And so this equation was the length is equal to the length of the m vector times the length of that constant times the b vector. So when you multiply, you might wonder, like, what? This guy's a number. This guy's just a number. So what that does is it just scales the vector. So if that was 1, you multiply 1 times the vector, it doesn't change the length. If that was 2, multiply 2 times the vector, you get twice as long for the vector. So, but that whole thing is a vector after you've scaled it with this constant. And find the length of that. So you find the length of the m, the length of the b, and then it's multiplied by the sine of the angle between them. And so here's that angle between them, the sine of that angle. So that's another. So the cross product involved multiplying all these individual coordinates of the vectors, but you can also the output that you get from multiplying all those coordinates is going to be equal to the length of these two vectors multiplied by each other and then multiplied by the sine. So we're going to need that for understanding how this equation works, because the sine is kind of hidden in that cross product sign. Cross product symbol has a sine sort of like embedded in it. Okay, so let's start off with what we talked about last time, which was just the basic precession operation. So if we start with so we start with, don't go off the top, that's the top, okay. So if we start with a b vector, so there's our b vector, and we'll start with, let me get a little bit longer. Okay, so that's about, kind of get about 4 of those. Yeah, that's good. Okay, so now we've got the m vector. So here's our m vector. So this guy, I'll label it with a different color. So this guy's the b vector. There's the m vector. So, and it's precessing around. So here's the little plane that it's whipping around on. And when we take the cross product of m and b, we figure out, so take your left hand and your right hand, go from m to b, and then that tells you that it sticks out toward you. And so that so here's that dm dt vector. So this guy is the dm dt vector. And for each small little fragment of time, this tells you, like what the next m vector will be. And then once you get that next m vector, you have to replug it into the equation, because now the cross product between the m vector and the b vector will have changed. It will have rotated a little bit, and it drives the precession around in a circle forever, if nothing else, if there's no other sort of change. So that's the starting condition. And so now what we want to do is, we'll call this I'll call it starting condition. We're going to mess with the different values to see how they affect it. So we want to see effects of change. So what order we'll do them in. So change M vector, change the angle, because there could be different angles. So here's the angle. That's the angle, the flip angle, and then change the B. So the first thing is, what if we just change the M vector length? So what if there's there's, for instance, more local magnetization? So let's just take a simple case. We'll just double the M vector. So we'll keep the B vector the same length. So just make the B vector the same length there. But now we've doubled the M vector. So here's the M vector. So I won't change the angle, and so I'll just double the M vector. So there's a bigger M vector. So M equals 2 times, and then here's B. So now what happens? So now what's going to happen is the M vector is going to be precessing around a bigger circle, like that, because there's the center of the circle. That's going through the center of the circle. So what is that going to do? What is that going to do to the dm dt? Well, if you just look at this equation right here, it's going to we just doubled m, so it's just going to double dm dt. So dm dt is going to be twice as big. So here's dm dt. So dm dt will get twice as big. Now let's consider how far it has to go around. So here's the old circle. The old circle was, it's down right around in here. That's the original circle. Well, the circumference of the new circle is just proportional to the radius, and we will have increased the radius by a factor of 2. So it's got to go twice as long, it's going twice as fast, therefore nothing changes. So basically when we change m length, circumference 2 times, so m 2 times, circumference 2 times, dm dt 2 times. What's the bottom line? Nothing changes. Same. So changing the m vector doesn't do anything. Now, as long as you kept the angle the same. So, angle the same. So, angle the same. So, yeah, so that's kind of weird. It's just, so why does it get canceled out? Well, it just gets canceled out because the m is on both sides. You got dm dt on this side, and you got m on this side. So if you increase one, it increases the other. So, but this is, that's all embedded in this equation, but to really understand it, you have to, like I said, you just have to you have to mess with it, just play with it, like let's fiddle with this and see what happens. Okay, so now let's do a little more complicated one. What if we change the angle? What does that do to the precession frequency? Because that's going to change the cross product. So let's change the angle. So we'll keep the B vector the same. We haven't changed that yet. So B vector is the same. But now let's change the angle and we'll go back to our old M vector. but just put it at a flatter angle like this. Okay, so what do? We change angle between M and B. So how do we change the angle? So we change the angle just by, changing the direction of the M vector. And then that, when you do all these funny multiplications here of the coordinates, that ends up with the sine of the angle effect. So we change the angle. So now it's a little more complicated. So now let's look at what happens. So now we've got a bigger circle than the first time compared to this first one right here. It's not as big as this one, but it's bigger. It's bigger. But we've got to sort of calculate, like, how much bigger it is. So basically, it's going to be proportional to the sine. So let me just make a little drawing over here. So if we've got something like this, what we want to figure out is, like, what is that radius? How far does the vector have to go around? And so what is that radius? That radius is going to be, so if this is the angle right there, this radius, that's the angle. This radius is just going to be the sine of the angle, because you've got a right angle there. It's a right triangle, and that's the opposite as opposed to the adjacent. So it's the opposite. Opposite as opposed to the adjacent. So the opposite side of the triangle is proportional to the sine of the angle. So the radius of this circle is going to be the sine of the angle. But if we look at what happens to dm dt, we will have, if we change this angle, we have to take that angle, put it through the sine, and so the dm dt is going to change by the sine. So what happens? So dm dt proportional to the sine of the angle. So what? Let's just sort of plot it out. So if you plot out the sine, so here's the sine. So it goes up like this, down like that, up like this, etc. So there's 0, 360 degrees, 2 pi, and so it's 0 at 180, and it's maximum at 90. So, and that makes sense, because and we said that's the way the cross product work. As you become perpendicular, the two vectors become perpendicular. That's when the cross product has the largest amplitude. And then if you continue down, it starts to go down again. So like as you continue down, it starts to go down, and then it reaches 0 when you're parallel. And then if you continue, this way, it's going to be negative. So basically, we're going to go up by the sine. So we started. We started here, say, at 45 degrees, and then we went up to, close to 75 degrees. So it's going to increase. It's going to increase dm dt. So here's dm dt. It will increase it, going up as the sine. But the circumference that it's going around also goes up as the sine because of this argument. So this is the circumference or radius. We just calculated the radius of the circle, radius of circle. So what's the effect? Nothing. So nothing happens again. So dm is proportional to sine, but the circumference is also proportional to sine. So end result, same. So surprisingly, changing the angle doesn't change the precession frequency. So no matter whatever we set the angle to, precession frequency stays the same. Whatever we set the length of the M to, you can make the M as big as you want, and the precession frequency stays the same. So what actually changes the precession frequency? So just the B, and we already had an equation for that. So let's just make the B a lot bigger. So I saved enough space down here. I got tons of space. So we'll make the B twice as big. So here's we'll make that nice big B. So if we increase the B, but we take the M back to what we had before. So here's the M, same as it was originally in our starting condition. So now here's the precession circle, which will be the same as the original precession circle. But now we just increased B by a factor of 2. So there's the angle. So what happens? Well, we increase dm dt by a factor of 2, because we just increased this guy by 2, multiplied this side by 2, that just makes this guy twice as big. So the end result is, let's make sure that one looks bigger, make it nice and big. So that's dm dt. So dm dt, so basically, increasing B increases, rate around circle, around same size circle. So, and we already knew this, because when we looked at, remember when we looked at the basic equation for the precession frequency, well, let's put the title here. So what this is, change B length. So basically, we knew this. So this increases precession frequency. But we already knew that. We knew that the precession frequency in radians per second, or equivalently 2 pi times the cycles per second, is just equal to this constant. Make sure I'm not off the board. Times, whatever the length of the B vector is. So if you've done a lot of math, you would say this is agonizingly slow, but I have not done a lot of math, and so it's about the right speed for me. So just trying to sort of understand, what the meaning of this equation is. So we change, so if you start off at a particular precession frequency, change the M length, doesn't matter. It just makes the dm dt bigger, and so it goes around a bigger circle faster, and then the rate of going around the circle, how many cycles per second or radians per second, is the same. Change the angle, and put the angle in here. So change the angle here. The angle changes dm dt as a function of the sine, but it also changes the circumference of the circle by a sine, and so they cancel each other out and nothing happens. And so then the only thing that changes things is if you change the B. So you change the B, and that's the only thing that changes the frequency. So this equation really sort of, you can sort of predict that equation from this equation. Okay, so I swore that I would take a little time to ask questions. So any questions so far on this? Just I'm I'm listening to you, so just speak up, turn on your mic and ask a question. And it shouldn't make it into my mic. So any questions out there? Cross product, everybody's okay with the dot product and the cross product and the complex multiply. We haven't used complex multiply yet. But this is, we're using the cross product here, which is it's that little x, but it stands for all those complicated multiplications of different components of the vector times each other. Okay, so just back up, what's the main point here? So we're just looking at, how these different things affect precession. So this is the first term of the Bloch equation. How does the first term of the Bloch equation, which is this thing work? Okay, stunned silence. Everybody's okay with it?
Everyone's okay with it. Thank you.
Okay. Okay, so let's go on then to the actual solutions to the Bloch equation for the other term. So what I've been so that's a good question. What have I been talking about? I've been talking about the solution to the Bloch equation. So I just drew it here as the derivative. This is like how you update the vector, but I didn't give you the actual solution, because the actual solution involves sines and cosines, because the actual solution will allow you to predict for a given point in time, where does the vector? That's what the solution means, the solution to this. So this was the differential equation, so distinguish. So this is the differential equation. But the solution is different. The solution will be solution, as a function of time. So the solution would be an equation that would have t in it, so that I could plug in, say, 2.4 seconds, and then say, where does it point at 2.4 seconds? That's what the solution means. The differential equation just says, for a small instant in time, small tiny little piece of time, what is it going to do next? But it doesn't give you the actual solution over time. I'll talk about that on the Friday graduate section. I'll talk about the actual solution to the precession solution, just to sort of see the gory details of how it works. I mean, it's very intuitive just looking at it this way, but to actually do it, you need sines and cosines and negative sine and cosine. So what we want to do now is talk about the T1 and T2 solutions, not how you get them. So I'm going to talk about that on Wednesday, how you actually get the solutions. But now we're just going to assume we got the solutions somehow. And what do they look like? So for that, we have to write out the whole Bloch equation. So I haven't written the whole thing out, so let's just write out the whole thing. So there's basically three parts of it. So the first part was the precession part, which is what we've done so far. And then the second part was the T2 decay. And then the third part was the T1 regrowth, or decay. Sometimes it's called decay, but we'll see it actually causes the vector to get longer in the z direction. So let's just write out the whole Bloch equation. So here's the whole Bloch equation. Definitely not off the board. That's good, Marty. Stay on the board. Okay, so the Bloch equation is equal to what we already did, m vector cross product constant times the b vector, whatever the b vector is. So that was the first term. And then second term is I'm going to write it out relatively. There's many different ways of writing it out. If you look in different textbooks, you'll see different notation. I'm just using this particular notation, which is mx times the I vector plus mx. I haven't defined mx yet, but I will in a second. My times the j vector divided by T2. So that's the T2 decay part. And so what we have to understand, so we have to understand several things here. There's like two vectors added to each other, and there's a T2 in the denominator. Why is it in the denominator? And then over here we look at the T1 term. So the T1 term is a little more complicated. So the T1 term has the Z magnetization, and then minus a constant. So this mz0 is actually a constant. And then that whole thing is multiplied by the k vector divided by T1. So that's the full Bloch equation. So the precession part, the T2 decay part, and the T1 decay part. But these are vectors. So they're essentially vectors adding to each other to generate a final vector. So we got so this is a vector. This thing is a. So that's just a number there. That guy's just a number. But since they're multiplied by these unit vectors, which we'll say what they are in a second, this is a vector. That's a vector. That's a vector. They're all three vectors added up to each other to generate a third, the output vector. So what is the? So there's the Bloch equation. So that's the full Bloch equation. So what does the mx business mean? So we can break up. So if we draw our standard coordinate system here, so here's the sort of x coordinate, and this is the y coordinate, and this is the z coordinate. So sometimes when you first look at this, you might think, why is the x coming out? You often think of x as kind of left-right, sort of just default way of thinking about it. Z is often up, but why is it this way? That's actually the same coordinate system as what I drew in the magnet. So if you look in the, if you look at the magnet like this, I might have said this before. The coordinate system was, remember, we had the z coming out this way, and then we had the y going up. That's kind of usually how you think of y. And then we had the x going left to right. So that's the same as this. Just like if you just take that whole thing and just rotate it 1/3, you'll get this. So this is actually the same thing as the coordinate system I was drawing in the magnet. It's just rotated with the z up. Now you might notice there's another possible coordinate system. What if we had the z pointing in the opposite direction? That's kind of like the mirror image coordinate system, but we're just going to stick with this one throughout the course. So there's you could have a mirror image coordinate system if the z stuck in that way and the x came out that way and the y came up. Sometimes that would be called a left-handed coordinate system instead of a right-handed coordinate system. But we'll try to stick throughout the semester with the standard, the same right-handed coordinate system. Okay, so now the problem is we want to get the solution to this piece of the equation. So now it's kind of like, yeah, we didn't even really talk about the solution. We just sort of drew that vector precessing around the precession part. But now we want to just somehow like screen those out of our mind, even though they're still in the equation, and just think about the solution to the T2 part. And we won't say how we got it. That's for Wednesday. We'll sort of explain why this is a solution. So we just write out the solution. And then there's one, before I write out the solution, there's one other thing that we're going to do, which is we're going to, for the time being, ignore the precession. So just pretend like the precession isn't happening. And one way of pretending that the precession isn't happening is to imagine that we're spinning around as fast as the precession. So if we spin around as fast as the precession, ourselves, the observer, then we can just sort of see the precession stopped. And that's often the way you think of this when you think of I'm doing a flip, and then some T2 decay is occurring. I don't think about the whole precession part of it. I just think of T2 as slowly decaying. And so that's often the way people think about it. We can actually show what that corresponds to in the math. But for the time being, we're just going to just say it, and I'll explain it maybe as we go along a little bit. So just pretend that we're spinning around as fast as the protons are, and so we can just see their length change in the xy plane without having to worry about all the fast spinning. So before I do that, though, I meant to sort of tell you what mx and my and mz are. And so basically, if you have some vector here, so here's a vector sort of like coming out at you a little bit. So say that's some m vector. So it's, think of it as sort of coming out toward you. So if we sort of project that down to the plane, then you're going to, let me just put that y a little bit further over. We can decompose that m vector into, so here's the m vector, decompose it into components, and that's what the mx, my, mz is. So if we get the, so here's the, so this guy's the mx, the x component of the vector, and then this guy over here, so that's this, and this thing is the my, and then we project onto the, also known as a dot product, project onto the z-axis, and here's the mz. So those things are just the xyz component of the vector. So those are numbers. And so then what is I and j and k? So I and j and k are just, so let's just say, we'll just do I. So I is just a vector that's a length of 1, pointing along the equals I vector. So that's the unit vector. So that's just a vector of length 1, just pointing along the x-axis. And then when we scale that vector by however much the mx value is, which is the this value that this point right here. So there's, put the mx right next to the top of it there. So that's just a sort of a wordy way of writing out the vectors. So numbers, a number scaling the unit vector in the x direction, a y number scaling the unit vector in the y direction, and then a z number after subtracting off this constant scaling the z component, the z unit vector. So the first thing is just look at this equation again. Just look at it and just sort of operate it with as if it was a little toy. So why is the time constant in the denominator? So the time constant, is like, if you know anything about MRI, you know that T2 is going to be like 50 milliseconds or 100 milliseconds, something like that, a tenth of a second. So why is it, so that's a time. So why is that time in the denominator? So it's in the denominator, just think about it. If this time is large, then you're dividing by a large number. And so what does that mean? That means the amount that you change the vector is small. So here's the change vector. So this tells you how to change the vector. So if this number is a large number, you'll divide whatever the current value of the x and y component of the magnetization by a large number, then you get a small number, then there's a small update. And that makes sense. So if you have a long time constant, a large time constant, it means that the update vector changes more slowly. Whereas if you have a short time constant, a small number, you divide by a small number down here, and you'll get a bigger number here if you divide by a small number. And so then that will make the rate of change more rapid. So this is, this is a time. So small means large change in dm dt. And large means small change. So that's why the time constant is in the denominator. So now let's just look at the solution. So the solution is, see if I can, I'll save space to plot it underneath so I don't have to erase. So let me just erase that. So give me a little bit more space. So if we just write out the solution, so again what we want, so this is the differential equation. And now this is the solution to differential equations, different thing. So the solution to the differential equation is just what is the magnetization in the xy? We're sort of glomming the x and y together, just for simplicity, as a function of time. So now we got no derivatives anymore. We just have what is the xy magnetization, the length of the xy magnetization, after we sort of, like, you imagine like you've got like a certain amount of x and a certain amount of y, and then that's going to be if this was, say, the x and the y plane, how much xy magnetization length do we have at any given time, and what is the function that describes that? And so the function that describes that is basically the amount of xy magnetization we have at a particular time over T2. Oh, sorry, no, that's not the solution, that's the differential equation. So it's going to be the amount of xy magnetization we started with. So what is this complicated mess? So this means the amount of magnetization that happened, and this plus stands for right after we did the RF pulse. So what this is amount of xy mag immediately after RF. So the idea is we do some kind of flip so that we get a signal, and then we don't allow the signal to decay at all, and we just say, like, okay, how much are we starting with? Now you may wonder, where did that come from? It's not in this equation at all. We just added it. So that's this isn't what's called an initial condition. We kind of added it, and so to understand where it came from, we'll talk about that on Wednesday, where it came from. But that's an initial condition. We just added that, and then the second part of the equation is we just multiply by e to the minus t over t2. So that's the solution. This thing is the solution to the t2 part of the equation. So where did this come from? It doesn't make. How is that a solution to this? How did we come up with that? I'm not telling you right now. We'll just sort of look at it. We'll just say this is the solution. So this has t in it. So there's the t. So this thing is just a constant. This guy is a constant for the purpose of this equation. It could be different things for different versions of the equation, but it's just a constant. It's just a constant, it's just a number, single number. And this one is also a single real number. Just, real. It's not a complex number. This is a real number. So that's the solution to the transverse decay, also known as the xy decay. And so then what is the solution to the T1 decay? So this is for T2. So here's a solution to differential equation for T1. And this one's a little more complicated. It's got the equilibrium magnetization. So this is how much magnetization you get if you go on the magnet a long time, times 1 minus e to the minus t over t1, plus our initial condition. So here's mz 0 plus, so the amount of z magnetization that we had immediately after we did the RF pulse, times e to the minus t over t1. Now there's another way to, so that's one way to write it out, but you can sort of multiply out the terms, and you can get a different way of writing it out. You'll see in some textbooks, which would be, mz0 plus, the terms multiplied out. So here's mz0 plus, that's that constant, that initial condition, minus mz0, which is the equilibrium magnetization, which is another constant, times e to the minus t over t2, over t1. So convince yourself that those are the same. Those are just another way of writing the equation. It's not nothing has changed. So this is another initial condition right here. So this is this guy, initial condition. So what does this look like now if we just plot this? So if we plot this over the next minute or two, I'll just plot this below. So I'll try to keep the y-axis, the x-axis, the same length in both of these. So if we plot, so as a function of time, so we're plotting this out as a function of time. So where are we starting? So we're starting at mxy 0 plus. That's the amount of xy magnetization we have. So let's just run this equation. So we stick something in there, mxy, whatever it is, and then we multiply by e to the minus t over t2. So what's t here? Well, t is 0. So what is e to the minus 0, or e to the 0? E to the 0 is 1. So this part just says 1. This part says whatever. So say it was 27, so then this would be 27. So if you run the equation, what happens is, you get something that falls off very quickly like that. So this might be, if we just put a time scale on here, this might be, say, 80 milliseconds. Less than a tenth of a second. So, and if we have a different T2, for instance, what if we have a T2 that is bigger? T2 is bigger, it's going to be making that exponent smaller, because it's dividing by the T2 is in the exponent. If you make the exponent smaller, it's going to cause it to fall off more quickly. So so this would be a larger so this is, oh, sorry, no, I said that exactly wrong. If we make a shorter T2, sorry, so this is shorter T2, so this is longer T2. So if you make a shorter T2, if you plug that into the equation and plot it in MATLAB, you'll see that a shorter T2, a smaller T2, causes a more rapid fall off of this equation, this part of the equation. It starts at 1, it'll more rapidly fall off. If you have a longer T2, a larger T2, you divide by a larger number, you get a smaller effect on the exponent, the fall off is less quick. Okay, so that's the equation for the decay in T2. Now if we do this other graph, this other equation for T1 is much longer. It's the value of T1 is much longer. So if we start off, say, at mz0 plus, that's actually negative. So here we only have positive here for the length of this vector. The length of the mx vector is only positive. But this guy could actually be negative. We could have actually flipped past 90. So if you look at this one, what this one will do is this one will go up much slower. Still, it's an exponential like decay, and what it's heading up toward is it's heading up toward mz0. And why is that? So let's just quickly, in the last -1 minute, just look at what this equation does. So if mz, so we have mz minus mz0. So here's mz0. So if mz is less than mz0, then that number is going to be negative. And then we take the negative of it, that makes it positive. So this term causes mz to grow until it gets up to the equilibrium number, which is mz0. In which case, when mz is mz0, it's mz minus mz0 is 0, and then there's no change. So that's why it's slowly but surely heading up toward mz0, starting from some point. And if we have a shorter T1, well, then it'll head up a little quicker. So it'll head up a little quicker like that. It'll still get to the same point. So down the line, it's just, it can only get up to the sort of the maximum number. So this guy is a shorter, smaller T1. This is a longer T1. And this is what the whole game of MRI is about, what we're trying to do. So these guys, notice, this one starts off at the same number here. This one starts off exactly at the same number. And so what we're trying to do in MRI is we're trying to get contrast between tissues that have different T2 values or T1 values. So what if we record the signal right at the beginning, there's no difference. And so what we're trying to do is let's wait until there's a good difference between the signals. If you wait too long, the differences will go away. The signal will go away and the differences will go away. The same thing is true here. That's what this equation implies. That if we start off right at I didn't plot this, I made it come up a little bit too quick. So it starts off very similar, and then it starts to get a little different, and then after a long time, it eventually gets exactly the same. So what we want to do here is also the same thing. Let's pick a time in here where there's a difference between these two types of tissues that we can actually try to exploit. So so we didn't say anything about how any of this works, how any pulse sequence works, nothing. It didn't say anything about like the rotating coordinate system, just the most basic thing. We have the Bloch equation. Here's the precession part that causes the thing to go around. Now let's just throw out the precession part and pretend it's not happening, and then we'll get the solution to the T2 part, which has this exponential decay, which somehow is a solution to this, which we haven't explained yet, but we'll do it next time. And then here's now we just ignore the T2 part. I'll try to explain why it's possible to ignore the T2 part. We just ignore the T2 part and ignore the precession part and say, how does this one work? This was a little more complicated. It causes these graphs here, and this gives us, again, when you look at this, this is, forgot to just put it in at the last second. So this is the mz as a function of time equals, yeah. So when you look at these equations, so this tells you how mz is at a particular point in time, and there's time right there, and there's time again right there. And this says, how does the transverse magnetization work at a particular point in time? And so then there's just one t right here. So when you look at these equations, you have to look at the variables that are sort of affecting the equation. So this guy has got 2 copies of time. Okay, so I've gone like massively over. So I'll leave the Zoom on, but we'll end the recording now just in time, David.